Hello everyone. In this video I'm going to be going over the wave equations, aka the nature of light. Um, I am sick. I explained this in the last video. I have a cold. I'm like recovering from it right now. So I am really congested, very nasally sounding, and I might sniff a lot in this video. I actually recorded this video before and I sniffed so many times that I had to delete it and make a new video because I was like, oh my god, I'm so annoying. Um, so my second shot at this video. Hopefully I'm not as sniffly, but apologies for that. So let's get into the wave equations, right? So let's look at the constants that were given, right? So these are all on the sheet that Professor Sherlock is going to be providing for us. But I just wrote them out here in some, nice pretty colors so they're easy to see. So the first constant that we're given is the speed of light in a vacuum. So we use the speed of light in a vacuum to help us with calculating these things. Technically, if you want to get like very technical with it, this wouldn't really apply in like the real world because we're not doing a lot of stuff in vacuums, but they do a lot of chemical reactions in vacuums. Like you can make your own vacuum, but when they're talking about a vacuum, they're more likely talking about like space and stuff. But either way, this is like the most ideal situation where C is equal to 3 times 10 to the 8th meters per second. Yeah. So that is the speed of light. And then, I sniffed. So this is Planck's constant, where it's 6.626 times 10 to the negative 34th. We use this to compare energy and frequency in order to find one or the other, vice versa, right? And then down here, these are the equations. Just want to make a note here that this equation and this equation are technically the same equation. There's just some algebraic manipulation there, right? So between this one and this one, all that happened was that they divided each side by f and then got the answer, right? So those are the same equation. You don't actually have to know, you only have to know one of them in order to do everything you need to with it, right? So the first one and the last one is saying that the speed of light is equal to lambda, which is wavelength in nanometers or meters. Most often it's in meters, because this is in meters per second, times frequency, right? Frequency is in 1 per second, or hertz. It's also sometimes denoted as like 1 minus or s minus 1. But either way, all mean the same thing. Hertz, s minus 1. Sometimes they call them like wave number or something. I don't know. But they all mean the same thing for frequency. The next equation is that energy is equal to Planck's constant times frequency, right? So energy in joules, Planck's constant is again just a little number that they came up with and figured out and did all these, experiments with in order to find the relationship between energy and frequency of a wave. So we're going to be using these equations throughout these next problems. Again, Professor Sherlock will be giving you these equations on your exam. Just a little side note is that for frequency, he uses nu, I think is what the Greek letter is. I like to use F because that's what we always use in physics, and that's what we did in like AP chemistry. So I always just use F because that's what I know, but use whatever is more familiar with you. I know a lot of other schools will use like different variables for frequency. There's like 5 of them that's used. I don't know why they do that, but there's many different letters that they use to represent frequency. I just use F because that's easiest for me. Okay, so on to the first problem. Let's do this problem here. So it says, what is the wavelength in nanometers of light that has frequency of 4.62 times 10 to the 14th wave numbers? So again, wave numbers, we're going to just say that that's frequency in hertz because that's what, that's what frequency is usually. So what we're given, I always like to write out what I'm given. So I'm given that the frequency is equal to 4.62 times 10 to the 14th nanometers. And then what I also like, that's not nanometers, it's 1 per second. 1 per second. Or hertz, whichever one you want to say, or wave numbers, whatever. And then we want to find the wavelength, right? So we're given frequency, we want to find wavelength. So I'm going to write lambda is equal to question mark. So then I know this is what I'm looking for, right? So the equation that we have to help us with that is C is equal to lambda F. The reason why I feel like this one is going to give us what we want is because, well, I know it's going to give us what we want because we know the constant C, so we don't have to worry about that. We know that number. We're looking for lambda and we have F. So because we have F and we have C, we can find lambda. So let's do that. So 3.0 times 10 to the 8th is equal to lambda, because that's what we're finding. F is 4.62 times 10 to the 14th. And then we're just going to divide. You could keep your units there. I like to have the units, so I'll add them in right now just to kind of check myself. So this is 1 per second, and then this is meters per second. So 4.62 times 10 to the 14th. 1 second. And those seconds are going to cancel out, so we're going to be left with meters. So that's good, because that's what we want. We actually want it in nanometers, but if we have it in meters, we can get it to nanometers. So I'm going to find it in meters first, and then I'm going to convert it. So let's do that calculation on our calculator. So we have 3 times 10 to the 8th divided by 4.62 times 10 to the 14th. And we will get 6.49. Your calculator might say something like 6.4935, blah, 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 blah. But sig figs is only going to get us to 3 because we only have 3 here. It's times 10 to the negative 7. So now let's convert that into nanometers. So we're just doing some dimensional analysis here. This is in meters, and there is that is not a straight line. I want to make that a little bit straighter. 1 times 10 to the 9th meters. So this is one that you might want to put on your 315 index card, is the conversion from meters to nanometers and nanometers to meters. So there is 1 times 10 to the negative 9th meters in 1 nanometer, and there's also, for 1 meter, there's 1 times 10 to the 9th nanometers, right? So if you know that conversion by heart, don't worry about putting that on there, but it is a good one to keep. I might actually put it on my index card because I know it's going to come to test day and be like, wait, what is it? And then I'm going to panic because I don't remember what it is, even though I should, because I've seen it so many times before. So our answer here is going to be 649 nanometers. So there's our answer for that question. Okay, moving on to the next question. Next question says, oh, don't want to do this one actually. It's one that I wanted to do but can't because we don't know photon stuff yet. Why? Oh, okay. No, we can't do this one. Alright, so this is the one that I want to do. Alright, so it's asking what is the wavelength? So I'm going to actually just write that. So we want wavelength again. And we are given the energy, which is equal to 1.51 times 10 to the negative 17 joules. Okay, so this problem, we're going to have multiple steps. I'm going to write the wavelength in nanometers just to give us that little extra step in there. Gives us some more conversion practice. So the first thing that we're going to do, and I'll explain why I'm doing this, is we're going to use this equation. The reason why we're going to use this equation is because this is the only equation that we're given that has energy in it and another constant that we know, right? So this is the only equation that we are given that will give us another answer, which will then lead us to the next equation, which has frequency in it and wavelength, so that we can find wavelength, right? So once we find F, we can use the speed of light equation to find lambda, right? So I'm going to use this equation first. So we're going to do 1.51 times 10 to the negative 17 joules. Oh man, I keep sniffing again. And then this number here, referring back to our sheet here, is 6.626 times 10 to the negative 34, and that is in joules times second. And we're going to multiply that by frequency. So what we're going to do is same thing as from before. We're going to just divide 626 times 10 to the negative 34 joules per second, or not joules per second, joules seconds. 6.626 times 10 to the negative 34 joules times seconds. We're going to cancel joules, so that means that we're getting this in 1 second, which will be frequency. That is the conversion for frequency. So we got 1.51 times 10 to the negative 17. We're going to divide that by 6.626 times 10 to the negative 34. That is going to equal 2.2, I'll say 279 times 10 to the 16. So yeah, again, when you're in the middle of a problem, the sig figs don't necessarily, matter. But then when you are, continuing to do the problem and everything, sig figs will matter. For your final answer. Sorry, I was like focused on something else. So in the middle of your question, sig figs don't matter. You want to deal with sig figs at the very end. So you want to get pretty much like as many decimals as you want to. Like for this problem, it was like 2.2789, and like that's close enough. This number is very close to that, so I'm going to use that number. Okay, moving on to the next calculation, we have C is equal to lambda. I want to say it's lambda f. I'm not actually looking at my sheet right now, so I probably should be. Yep, it is lambda f. Cool. So we're going to do 3 times 10 to the 8th is equal to meters per second, is equal to lambda times that frequency that we just got, 2.279 times 10 to the 16th. And same thing as before. This is in 1 per second. 1 second. We're going to divide. Same thing as the last problem that we did. Times 10 to the 16th. 1 second. I'm like chicken scratching this right now. I usually have very neat handwriting, but I get, the famous quote, they don't pay me for my handwriting, but they don't pay me at all. So, okay. And our answer for this part is going to be lambda is equal to, we have 3 times 10 to the 8th. We're going to divide that by 2.279 times 10 to the 16th. Lambda is going to be 1.31, let's do it in sig fig, so it's 1.32 times 10 to the negative 8th. And now I'm going to take this, I'm going to convert it over here, 1.32 times 10 to the negative 8th. This is meters, because this is the unit that we have, meters, by 1 times, there's 1 times 10 to the 9th nanometers in 1 meter. And our final answer is going to be times 10 to the 9th. It's going to be 13.2 nanometers. I'm like blanking. I was like, what comes after that? Nanometers. So that is our final answer for that problem. Thank you all for watching. Again, apologies for all the nasaliness and everything like that, and just brain fog going on. But I do appreciate you all watching these videos, and good luck. Let me know if you have questions.